looking out on the morning rain.
Before we try to discover what the derivative of natural log of x is, let's just refresh our memory. What is a derivative? That's right, a derivative is a slope of a function at a point, or the instantaneous rate of change of a function at a point. The derivative can also be a function in its own right. It's the collection of all of the slopes. So for example, let's just sketch f prime of x. So at this point, the slope of this function is negative something. Boink. At this x value, the slope of that function is still negative, but less negative. Boink. Right here, the slope of that function is 0. The derivative is 0. Let's see right here. The slope is positive. Here, the slope is even more positive. You see, I'm sketching some little tangent lines. If I connect all of these points, I will have the derivative. Now I'm assuming that my original function here was quadratic, and therefore its derivative would be a line, because we know that the slope of a quadratic changes at a constant rate. Very cool. Let's do the same thing with y equals e to the x. Let's think about the slope of this function at various points. Well, the slope there is positive, not very steep though, so maybe a small positive number. The slope there is a bigger positive number, and bigger, and bigger, and bigger. Now, if you remember, we actually discovered that the derivative of e to the x is exactly e to the x. That was that mind-blowing, beautiful thing that we discovered. That the y value of e to the x is exactly equal to the rate at which it's changing at that place. So cool. All right, so now let's turn our attention to y equals natural log of x. Why don't you pause the video and try to make a sketch of what you think the derivative of the natural log of x is going to look like. All right, how'd you do? So let's see, I'm just going to go piece by piece. That looks like a positive slope there, positive, getting less 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 positive. So my slope, my derivative started off really positive and is getting less and less positive. Doesn't look like it's at a constant rate. And I'm pretty sure that that slope is never going to equal 0, because the natural log of x, if I input bigger and bigger x's, I'm going to get bigger and bigger y's. So that keeps going up, up, up. Natural log of x is an increasing function, and so its derivative is never going to equal 0. Kind of cool. We know that the domain of the natural log of x is all real numbers greater than 0. Remember, that's a logarithm, so it doesn't make sense to take the logarithm of 0 or of a negative number. So I have a restricted domain of my original function, and therefore a restricted domain of the derivative. Okay, so I figured that out graphically. So again, pause the video and think about all the functions you know, and see if you can come up with a function that might look like that green derivative we just sketched. Did you come up with some ideas? Well, we're going to discover it together. What is the derivative of the natural log of x? All right, this is a little tricky, but you guys are all smart whippersnappers. Pause the video again and just see what you can do with this. Play around with this and give yourself a little bit of time. If you have a compatriot, discuss different ideas you have to try to take the derivative of that. If you get stuck, I'm about to give you a hint, but think about it before you listen to the hint. Ready for your hint? Your hint is to remember that logs are exponents. So can you rewrite this? Can you rewrite y equals natural log of x in its exponential form. And a little reminder, remember, natural log of x is really a shorthand for log base e of x. Remember, there's a little invisible e there. So your hint is to rewrite this in exponential form and then take the derivative. See what you get. Pause the video.
Feel uninspired.
Okay, how did you do? So I first rewrote this in exponential form, and then I took the derivative of both sides. Careful, you have to remember to use implicit differentiation here. And don't forget the chain rule. The derivative of e to the y is e to the y, chain rule, times the derivative of the inside, times the derivative of y, which is dy dx. What's the derivative of x? 1. Now if I want to solve for dy dx, I get 1 over e to the y. Woohoo! You found the derivative of natural log of x. But what looks unusual about this? Yeah, I have my derivative in terms of y, which is okay, but that might get a little awkward. So now try to rewrite this derivative in terms of x. I'll give you a hint. Everything you need is on this page. Just look back at your work and rewrite this derivative in terms of x rather than in terms of y. All right, how was it? Yes, if you look back at your page, what do you notice? Da 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 da. Look at that. Right up there, it says that e to the y equals x. So can't I just replace that e to the y with an x and say that dy dx equals 1 over x? And yes, you can. And that is the derivative of the natural log of x. The derivative of the natural log of x is 1 over x. So let's take that one step further and write the rule in a way that recognizes that the chain rule will also come into play frequently. So if we let u be an expression in terms of x, then the derivative with respect to x, remember this just means I'm taking the derivative of this and x is my independent variable. The derivative with respect to x of the natural log of u, right, is 1 over u, that we just discovered. Then here's the chain rule part, times the derivative of u. This is the chain rule right there. And lots of times we write the rule with the chain rule embedded in it so that we don't forget that chain rule. So here's a quick example. If I want to take the derivative of the natural log of x squared plus 1. Okay, so here's my expression u in terms of x. So the derivative of the natural log of something is 1 over that something. That's what we just discovered. And then times the chain rule, times the derivative of the inside, which is 2x. And then we could simplify this, of course, just by saying that's 2x divided by x squared plus 1. Okay, that's not too bad, is it? That's not too bad. Let's do some examples. Okay, pause the video for each one of these examples and do it, and then see how I do it. So give this one a try. Da 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 da. I hope you got that. Don't forget, you have to write f prime of x. If you just write equals equals equals, it's totally wrong, right? This is the function. This is a new function. This is the derivative function. So it's 1 over that something, and then chain rule times the derivative of that something. Try this one. Here we have a coefficient. Give this one a try. Et voila! Remember, our coefficient can just hang out. The derivative of a coefficient times a function is just the coefficient times the derivative of that function. Here's my derivative. I simplified, multiplying the 7 times the 3, and there we go. Try this one. Take the derivative with respect to x. Wow, this one was so long I had to pan out. So this is the product rule, a, b. So the derivative of a prime, so that's the natural log of the base times the exponential term as it is, and the chain rule times 2, times b as it is, plus a as it is, times the derivative of that, so that's 1 over the sine of 5x squared. Chain rule, chain, we have a couple links, times the derivative of the inside, so the derivative of sine of something is the cosine of something, and then an inside of that, derivative of 5x squared is 10x. Not a whole lot to do to simplify. I mean, I could put cosine of 5x squared times 10x in the numerator there. Not a lot you could do. If you felt like factoring, you could factor out a 6 to the 2x minus 1, but that doesn't really simplify it much. Take a look at this one. Now I'm going to give you a hint. There's a long way to do it and a short way to do it. Think about what you remember about logs, and perhaps what you remember about composition of functions. All right, let's do this the long way, and then let's do it 2 shortcut ways. So the long way would just be to do our rules. So this is the natural log of something, right? That implies the parentheses are there. So the derivative would be 1 over that something, right? Times the derivative of that something. Well, the derivative of e to something is e to that something. And then times the chain rule, 3. Ooh, look at that. That just simplifies to equal 3. That's cool. So that was the long way, and you might be thinking, well, that wasn't that long, and you're right. So method 2, maybe some of you saw this, is to remember something about the rules of logs. And if you recall, since logs are just exponents, if you have the log, let's just say it's a common log, log base 10 of 3 squared, let's say, that's the same as 2 times the log of 3. Right? And actually, since we're using common logs, let's pick a nicer number. And then we can see that it's intuitively correct. So if I say log base 10 of 10 squared, that's the same as 2 times the log of 10. And you can quickly think, all right, 10 squared is 100. There's a little invisible base of 10 here. 10 to the what equals 100? Oh, 2. The log base 10 of 10 is 1, because 10 raised to what is 10? 1. 2 times 1 is 2. So you can see intuitively that those are the same. What in the heck does that have to do with this? Well, what that means here, I could, before I do this, I could rewrite this as 0.3x times the natural log of e, right? In other words, you can bring that exponent down. Well, what is the natural log of e? Oh, well, again, natural log is a log with a little invisible base e. This is saying e raised to what is e? E raised to the 1 is e. So the natural log of e is 1. And that means my function is 3x. And what's the derivative of 3x? It's 3. Okay, I called that a shortcut, but I guess that wasn't all that much shorter than this. But let me show you a real shortcut. So the third way to do this problem is to remember something about compositions of inverse functions. So let's just remember, when you have a composition of 2 functions that are inverses of each other, whatever you put in for x, g of x does something to it, then f of x, if it's the inverse of g, is going to undo whatever g did, and you're going to end up with what you started with. A nice example, if your function is x squared and its inverse is the square root of x, if you take the composition of f of g of x is square root of x, f tells you to square the square root of x, yeah, you end up with x. If you recall, if I have a function e to the x, its inverse is the natural log of x, right? Here's e to the x, here's y equals x, there's natural log of x. They're inverses of each other. So if I do f of g of x, whatever I put in, I'm going to get out. Does that help you now? With method 3 of this function. So now when I look at this, I say, wait a minute. I'm putting an e to something inside of a natural log. Natural log and e are inverses, so they undo each other. So I'm just going to rewrite this function as y equals 3x. Holy cow! So the derivative is just 3, which of course is what we got using the other two methods. That is the quickest of all. So with that in mind, take the derivative of this. Pause the video. Okay, are we back? Again, you could do it the long way, take the derivative, but let's do it the short way. E to something and the natural log of something are inverses. So they undo each other. So I'm just going to rewrite this function as 3x, and the derivative is just 3. Love that. All right, I hope you enjoyed the derivatives of natural logs. You make me feel like a natural log.
I'd have to face another day.